Greetings, physicists. This video will be about how to solve kinematics problems that occur in two dimensions at once. So, we'll start with this one. We've got a bird flying along for one interval. He's going to change his direction and go for another interval. And they give us some numbers and some directions, and they ask, what is the bird's net displacement? And remember, displacement is from where you start to where you end. So I'm going to go ahead and draw this one. Let's give ourselves a little, don't do that. Let's give ourselves a little compass rose. North, south, east, west. And he starts by going 100 meters due east. Here we go. 100 meters. Assume that line is straight due east. I'll do it as a vector because it's got a direction with it. Then 200 meters northwest. That is 45 degrees north of west. And by the way, if this statement hadn't been there, and they just say 200 meters northwest, you will assume that's a 45-degree angle. There's no other way to interpret that. Northwest is halfway between north and west. Northeast is halfway between north and east. Southeast, etc. Always a 45-degree, unless they say 30 degrees north of west or something like that, which is much more specific. Okay, so I need to go north of west. Well, west is this direction, so I need to tilt north of that, which is that direction. So when I'm kind of backtracking here, I'm going to go 45 degrees like that, but this is a longer 200-meter long arrow. And I've drawn them head to tail, right? I end one vector and then I start the next one. That's how you're going to add your vectors. Okay, what is the bird's net displacement? Well, his net displacement is from here to here. And we start at the tail and end at the tip. So that is his displacement vector. I don't know if if it's actually going to be to the left of the starting point because I just freehand drew that. But let's see how we're going to deal with this. Well, I want to resolve everything into an xy plane. And right now, this 100-meter vector is already in the xy plane, so he's easy. He's just 100 meters this way. The 200 meters, though, is going between. In fact, he's exactly at a 45. So the nice thing is his component vectors will be equal, but he has a component that's left and a component that's up. I should say a component that's west and a component that's north. And his 200 meters is there. So we have an adjacent leg and we have an opposite leg. So the adjacent leg is 200 meters times the cosine of 45, and the other one is 200 meters times the sine of 45, and luckily for us, those two numbers are the same. Sine and cosine of 45 both end up being 2 root 2, I think. Alright, so let's do this. Calculator 200 sine 45 or cosine 45, either one works, and I get 141. So if I'm going to redraw this, I now have three vectors. I have a 100-meter vector that goes to the right. I have the horizontal component to the left of 141 meters, and I have a vertical component vector of 141 meters, and I should have drawn those longer than the 100-meter vector, obviously. That's my bad. So what can I do here? Well, this vertical vector is the only one of his kind, so nobody can make him longer or shorter. However, I have a 100 to the right and a 141 to the left, and those will subtract from each other. I can make one positive and one negative. Let's just make the 100 negative because he's smaller. So what I'm left with when I subtract them is a leftover of a 41-meter vector to the left. So if I draw the leftovers here, the net leftover vectors are just 41 meters horizontally to the left, or to the west, you could say, and 141 meters vertically, or to the north. And I have not added them properly. This is just showing you what they look like. If I add them, I have to do them head to tail. So this would be 41, like so, and 141, like so. And then my my resultant, which is the actual displacement from start to finish, is from start to finish. And so what I really need is that magnitude and this angle. Or this angle is fine, but I'm gonna go ahead and go for the one I drew. All right, well, if you could solve triangles, there are a number of ways to do this. I'll do the 41 squared plus 141 squared square root to get the magnitude. So 41 squared and 141 squared and square root that, and I'm getting very close to 141. 147. So this is 147 long. And then I need the angle, and I think the angle can best be done 47 meters. Then I need that angle, and I'm going to use the tangent here. So we'll do tan theta has to be equal to, if that's the angle theta, then this is the opposite and this is the adjacent. So tangent equals opposite over adjacent. So I'm to solve this, since I have the opposite and adjacent, I'm going to do an inverse tangent of opposite over adjacent, or 141 over 41. So let's see what that comes out to. 41 divided by 41, and I get 74 degrees if I round. Fairly vertical. Yeah, we expect that, right, because this is longer than this one. Okay, so to put that into a statement here, come on, here we go. That bird winds up traveling that distance, which is 146 meters at an angle that is 74 degrees. And let's say where we're measuring it, that 74 is measured above west, so that's north of west. We're rotating this way from west. We're rotating to the north side of the west vector. Yeah. 146 at 74 degrees north of west. You could also say that this is equivalent to saying 146 meters at an angle that is, if that's 74, then this is 16 degrees. So you could say at 16 degrees, but that's the other direction. That's west of north. So either of those are equivalent. Okay, let's go to the next one. All right, we've got a car driving up a steep 10-degree slope. Probably you don't think 10 degrees looks very steep, but driving it, you will feel it. At a constant speed of 15 meters per second, which is about half of highway speed. It's about 30 miles an hour or so. After 10 seconds, how much height has the car gained? So let's draw this. Let's draw a 10-degree slope. 10-degree slope is actually probably less steep than that. And the car is driving this way at a speed of 15 meters per second. And it does this for a delta time equal to 10 seconds. So I'm just writing my givens down here. And we're curious about the height he has reached after 10 seconds. Well, the height he's reached will be this. Notice how this becomes the vertical leg of a triangle. So we're looking for this height, this x here. Well, we have, this is essentially an opposite leg to this 10-degree angle, and this is a right angle, right? A vertical line makes a right angle with a horizontal. So if we just knew the distance from here to here, we would be able to figure out, we would have a hypotenuse and we would have an opposite and we would have an angle. We could solve this triangle. So let's figure that out. Well, that's a distance. We need an x, and we have a velocity and a time. And we know it's a constant speed. So we can do v is delta x over delta t, but we're looking for delta x, so delta x would be equal to v times delta t, and we have both of those. That's 15 meters per second times 10 seconds. Seconds will cancel, and I will get 150 meters. So I can label that there. That's 150 meters, and now I just need to solve my triangle, because I have a 10-degree angle. I have a hypotenuse and an opposite, so that it looks like a sine function. Remember your SOHCAHTOA. So sine theta equals opposite over hypotenuse. And I'm looking for the opposite. The opposite is what I'm looking for. So let's solve for that. So we're going to have h sine theta equal to the opposite. And that's where I need to be. So let's plug things in. Let's plug in x is what I'm looking for. H, the hypotenuse, was 150 meters times the sine of 10 degrees. And make sure your calculator's in degrees for this, obviously. So we'll do 150 sine of 10. And that, in my calculator, comes out to 26 meters, which is what we're looking for. 26 meters up is how far you go if you drive 150 meters along a 10-degree incline. Good to know. Moving on. Speed skiing. Dangerous stuff. Let's see what they're asking here. The Willamette Pass ski area in Oregon. It's apparently where we hold these competitions. And we go down a constant slope, or a reasonably constant slope. You can only do so much with nature. And you're trying to get as fast as you can by the time you get to the end of the area they've marked off. And in this case, they traveled 360 meters and only dropped 170. How fast could they have been going by the time they got to the end of that ski run? So we're looking for a maximum here. So let's try and draw it. They dropped a total vertical distance of 170 meters. That's, I think, the easiest given that they give you. Then they say, during the acceleration phase, the skiers traveled 360 meters. Now, there's an interpretation to be made here, whether we think that is the horizontal distance or whether we think that is the angled distance. I'm going to say I think that's the angled distance. I think they traveled like that, 360 meters. So whatever the horizontal distance is, we don't know. But it may not be important. So, what is the fastest speed a skier could achieve at the end of this run? So let's think about what we know about angled surfaces. If you're traveling on an angled surface, right? An incline that's inclined at some angle theta, and you're here, gravity tries to pull you down this way, but there's a surface in the way. So what really happens is you only get part of gravity. Right? You get the part that actually pulls you down, your box, down the incline. And what I recommend is that you rotate your incline theta degrees this way. You rotate theta degrees. This is not like, this is a visualization tool so that it looks like this thing is going to the right. And then you'll see that your G has also rotated by theta degrees, and it's rotated in this direction. So it was theta degrees from the vertical. So that's theta, and that's G. And what you will see then is that your G has a downward component and a horizontal component, and that horizontal component is opposite of this angle. So what's accelerating you is G sine theta. So the maximum speed the maximum acceleration that these skiers could get is G sine theta. This is assuming that the snow is very slippery and that there's no friction with their skis, which is close, but not quite perfect. So here's what we're going to do. We have some givens here, right? We know that the distance they travel is this. They travel 360 meters at an acceleration of G sine theta. So we have a delta x, that's a given. We have an a, that's a given. But they also gave us a v, or v naught. They said that these skiers start from rest. That's 3 givens in a kinematics problem, which means that we will be able to find at least one equation for what we're looking for. And what we're looking for, our unknown, is final velocity. So we have ax v naught, we want v final, and that should bring up this equation, that v final squared is equal to v initial squared plus 2a delta x. And if I solve for v final, that's going to be the square root of this. Well, notice that v initial is 0, so that can go away. So it's going to be the square root of 2a delta x. All right, let's plug in what we know. Square root of 2, a in this case was g sine theta, or 9.8 meter per second squared times the sine of theta. Ooh, we're going to have to do a theta calculation. We'll just put theta there for now. And the delta x was 300 and something. Let's look. What's my delta x? 360. 360 meters. Okay, so I just need to know what my angle is here. So let's go back to this triangle. Let's see if we can solve this triangle. Okay, so we're looking at this angle theta here, right? That's the one I need when I do g sine theta. So if I look at that angle, then this 170 is the opposite angle, and this delta x is the hypotenuse. So this looks like a sine. So we have sine theta equal to opposite over hypotenuse. So I'm just doing the inverse sine of the opposite over the hypotenuse. And so this is going to be sine minus 1 of 170 over 360. You could do that in your calculator. I don't recommend you do that, because you already have that the sine of theta equals this, or equals 170 over 360. So just replace the whole thing. Look down here. This down here. See how sine of theta is its own piece here? So we're going to do this. Square root 2 times 9.8 meters over second squared times 170 over 360 times 360. Hey, that's going to make things easy, isn't it? Because the 360 will cancel. There was a meters there as well. So what I'm really doing is the square root of 2 times 9.8 times 170. So let's see what that is. Square root of 2 times 9.8 times 170 equals 57.7. All right. 57.7, and we have a meters times a meters, that's a meter squared over a second squared, and we're square rooting that, so that's a meters per second. And if I'm looking at sig figs, I think these are all 2 sig figs, so let's round that to 58. So these skiers are getting up to, at maximum, this is assuming no friction, they don't turn any, and you know, this is going to be 58 meters per second that they could get, which is about twice highway speed. So if highway speed is around 60 miles an hour, they're going about 120. That's pretty quick. I have no interest in becoming a speed skier. That would be one of the more dangerous things that your mother probably tells you not to do. Son, daughter, don't grow up to be a speed skier. All right, last one. What a roller coaster. And we have a roller coaster that looks like this. Goes down a big first hill and then up over a second. So hill and up over this hill. What are we saying? We have the second hill has a slope of 30 degrees. And at the bottom of the hill, down here, the coaster cars are going 25 meters per second. And to get up over this hill from point A here to point B here apparently takes 2 seconds. And we're curious at point B here, when they get to the top, how fast are they going? So let's label some stuff that like I did here. This 25 meters per second looks like a V initial. This 2 seconds looks like a delta time for that interval. All right, and then the question they're asking is how fast are they going at the end? So that's a V final. That's our unknown. We need another given for this, and I think that given is going to have to be based on acceleration. So we're assuming that the slope from point A to point B is a fairly even 30 degrees, even though I drew it with some curved starts and ends. But let's ignore that and say that that slope is exactly 30 degrees. So we can draw a 30-degree slope that the roller coaster is going to travel on, the car will travel on as it goes up the coaster. So we could figure acceleration, right? The acceleration is going to be back this way down the slope, and just like before in the previous problems, it is a g sine theta. So g times the sine of 30. Good, and that's our acceleration. And we know theta is 30 and we know g is 9.8, so we have all our givens, I think. So let's look and see here. We have acceleration, v naught, and delta t, and we're looking for a v. So the equation we're going to choose, if you look at your list, let's go through it. I believe this one makes the most sense. But I have to be careful, because if you think about it, the acceleration like I've drawn, is here. It's in the reverse direction, but the velocity is in this direction. So you will have to make one of those negative. I'm going to go ahead and make the A negative so I don't mess up the signs. Very important that you reconcile that. So V is what I'm looking for, so I don't even have to rearrange this equation. So V will equal V naught, which they told me at the bottom where it starts going up the ramp is 25 meters per second, and I'm saying that is the positive direction. Plus, except that it's going to be minus, because I'm saying acceleration is minus my G, which is 9.8 meters per second squared, times the sine of 30, times the delta time, which is 2 seconds. All right, and now I can just plug that into my calculator. 25 minus 2 times 9.8 times the sine of 30. Times 2. Oh, I already did the 2, didn't I? Okay. All right, and I'm getting left over about 15.2, and that should be, so this was meters per second squared, and this was seconds, so 1 seconds will cancel. I'll get meters per second minus meters per second. Important that we have the same unit. So this should be in meters per second. You can only add or subtract like units. Sig figs wise, did they give me 25 originally or 25.0? They gave me 25, okay, and 2.0. So this is all 2 sig figs. So I'm actually going to round here to 15 meters per second. Okay, so those are several different types of two-dimensional problems. We had incline problems and we had motion in two directions problems. And hopefully this sets you straight on how to solve problems of this type.